For those who I know pretty much almost everybody here, but for those, the new agents, I introduced myself. My name is Maria, again. I'm a soil scientist. I've been in this position for about almost 11 years now. When Joe asked me, and I knew there were going to be a lot of familiar faces in this room, so I didn't want to go over the same slides again. So my intention during this presentation is to go over some of the more concepts, and I'm also going to try to do some more practical examples on how to interpret soil tests and some of the concepts that we need to learn so we can understand the soil test results better. That's the intention of today's presentation. By the way, I understand this is going to be quite a long morning section, so feel free to stand up. And this is very informal, even though we are recording. I think this is very informal. And feel free to interrupt me at any time if you want me to repeat or go over. If you have any questions, we're going to have a 15-minute question section at the end of the presentation. But if there's anything or any question during the presentation, please feel free to interrupt me at any time. So the title of my presentation is Principles of Nutrient Management, and I want to start by defining what is nutrient management. We hear that term so frequently in different disciplines, not only soil science, but a lot of people use that term nutrient management. And can have the term can have different meanings depending on what the goal is. For my goal, I'm defining nutrient management as management practices that can keep the nutrient cycles in balance. So some nutrients, they cycle through different interfaces. They can be present in the soil, they can be in the plant, they can be consumed by animals. Some are also have gas forms, they interact with the atmosphere. And usually in undisturbed system, those cycles are balanced. But there's hardly any undisturbed system in the planet. So everything is pretty much disturbed by different causes, but everything is pretty much disturbed. So the problem is when we start managing, we change that natural cycle of the nutrients. And usually what happens is we end up with nutrient deficiency in the soil, or we can have environmental problems, water quality problems, air quality problems, all sort of unintended consequences because we break that natural cycle. And the cycles can be very complex. Don't worry, I'm not going to go over this cycle, but this is the nitrogen cycle. Nitrogen is a very dynamic nutrient. When you look at, for instance, if we were to compare nitrogen cycle with phosphorus cycle, phosphorus is a little bit simpler. It doesn't have so many compartments. So if you look at in the soil, for instance, just the soil compartment, nitrogen undergoes so many different transformations in the soil, and that will affect how efficiently the plants can use nitrogen. Nitrogen is also subject to gas losses, volatilization, and denitrification. So there's all these things happening at the same time in the system, and we're trying to manage from the point of view of nutrient management. So usually, why those natural cycles are broken? Because we exceed the removals, whether it's crop removal or animal product removal, so we're exporting much more than what is entering into the system. Losses can be another way to disturb that natural balance. So losses like leaching, runoff losses can also shift that natural cycle. And other things like increased atmospheric deposition, for instance. For some nutrients, atmospheric deposition contributes to a significant proportion of the nutrients that are present in the soil. So that's why I said there's hardly any undisturbed system. By disturbance, I'm not meaning only human disturbance, but atmospheric deposition can increase, for instance, nitrogen concentration in some ecosystems. So we're shifting from the natural ecosystem that all these cycles were balancing to a more unbalanced system. So when we introduced the concept of nutrient management, we're talking about, in this particular case, like I said in the beginning of the presentation, we're talking about soil nutrient management. It could be other things. So usually we use the words soil nutrient management and soil fertility almost interchangeably. They are not necessarily the same thing, but we're going to talk about that as well. So the greatest impact when we manage our soil in terms of nutrient is usually not necessarily felt in the soil or in the plant response, but it usually is felt in the ecosystem, particularly in the water quality. Now switching over from nutrient management to soil fertility. Usually when we manage the soil, usually we target at improving the chemical properties of the soil. So we lime the soil, we add fertilizer because we want to improve the chemical characteristics. The chemical properties are going to affect plant response, how well the plants can produce in that particular soil. But there are other properties, physical and biological properties, that are equally important. And we're going to talk about that as well. But when we, from the practical perspective, we don't manage physical properties, or we very rarely manage the biological properties. So for the purpose of today's presentation, we're looking at the chemical properties specifically. So what are the typical steps involved in that nutrient management with the target of improving the chemical properties? So there are different steps that are involved in that nutrient management. One of them, those three that are highlighted in yellow here, are the ones related to improving soil fertility conditions. So we take soil samples, plant tissue samples, and based on the nutrient analysis, we can determine how much nutrients need to be added to the soil, or soil amendments need to be added. If we are using organic amendments as fertilizer sources, we also need to know the composition of those amendments. For instance, nitrogen. Nitrogen, we don't use soil tissue test analysis to determine nitrogen fertilizer application. So we have to determine what is my goal, and those yield goals need to be realistic. So anyway, I'm not going to go over all of these details, but it's a very complex process. And typically, when we mention soil fertility, we're only looking at these three components. But the reason I want to show this slide is to tell you that there are more factors involved in the nutrient management. And I'm pretty sure some of the other speakers are probably going to talk about grazing management, grazing strategies that can also affect how nutrients are distributed in the pressure, that it can also affect the chemical properties and how well the soil can provide nutrients back to the plant. So let's talk about soil fertility in more details. In order for us to understand what soil fertility is, and well, Andrea told me not to move too much, but I guess I'm moving all over the place. We need to understand what is my intention when I'm managing soil fertility. So the first thing we need to learn is there are 17 essential elements, and they are considered essential because they meet these three criteria here. So in other words, the plants cannot complete their life cycle if they're not present. That doesn't necessarily mean that they need to be added as fertilizer, but they need to be present. The majority of them comes from the soil. Out of the 17, 14 comes from the soil. So you've probably seen, let me skip to the next one. I'm going to talk about this slide first. You've probably seen some commercial fertilizer like this. I blocked to purposely block the commercial name of this particular product, but they claim they contain almost the whole periodic table. And they sell this as being an advantage. So anyway, why we need, with the concept of essential nutrients, why do I need lithium in my fertilizing mix? Probably it's not going to have any impact in terms of plant production or plant persistence or anything. But they use this as a marketing strategy. Well, when you buy traditional fertilizer, you're only buying nitrogen, phosphorus, and potassium. But here, you can buy dozens of these nutrients. But when you look at the concentration, basically you are applying water to your soil. So the nitrogen concentration, I understand this table is fairly small, so that's why I'm enlarging here the concentration. So nitrogen, for instance, somewhere in here, nitrogen, 500 parts per million, this is equivalent of 0.05% of nitrogen. So imagine, even for forage crops that usually have a very relatively low nitrogen requirement compared to other crops. So imagine established barreras, 60 pounds of nitrogen to the acre. Imagine how much of this material you have to apply to supply just the nitrogen demand. So there's a lot of products like these that they claim they contain more nutrients, but there's really no scientific evidence that some of these nutrients can actually benefit, the plants can actually benefit from application of these nutrients. The other thing I want to go back to this slide is, so these are the 17 essential nutrients. They are classified as macro and micronutrients depending on how much the plants use. It doesn't have anything to do with how important they are. They are equally important, but the micronutrients plants use in very small amounts, and usually the soils can supply those micronutrients. Very rarely, especially in a grazed system, we very rarely worry about micronutrients. There's actually no university-based recommendation for micronutrients in grazed pastures. But the macronutrients, which consist of nitrogen, phosphorus, and potassium, because the plants use in large amounts, and because our soils, the chemical properties of our soil in Florida, we have to supply, typically we have to apply fertilizer because the soils are usually deficient in one or more of these nutrients. So the other important, I know that I'm probably going over my time, but the other thing I want to point out in this slide is the forms that these nutrients are absorbed. So it doesn't matter if you apply manure, biosolids, ammonium nitrate, ammonium sulfate, nitrogen is always going to be absorbed as ammonia or nitrate. So the only difference is if you're applying an organic fertilizer, the nitrogen will have to go under a process that's called mineralization, which in other words converts organic nitrogen into inorganic nitrogen, so in these forms here, and the plants can better utilize. And the same thing is valid for the others. So it doesn't matter, for the plant perspective, it doesn't matter if the nutrient is added as an organic fertilizer, as an organic source, or inorganic. The chemical form that this nutrient will be used by the plants are always the same. So usually the nutrient requirements of a specific forage crop species is related to their yield potential. So in other words, plants that, species of cultivars that have greater yield potential, they usually require more nutrients. In this case, I'm focusing on nitrogen, phosphorus, and potassium, and this is the amount of nutrients removed to produce that amount of forage. So Jinx, Bermuda grass, and some of the other Bermuda grasses cultivars, they produce more, but of course they require more nutrients. So in other words, from the practical perspective, let's look at here, Bahia grass. Bahia grass can produce about half of what most of the Bermuda grasses can produce, but it also requires half of the nitrogen. So a very common situation, a lot of producers most people don't have one single species, but if they manage the same way, they might be setting themselves for some trouble because the requirements of these different species is different. So if you manage a Bermuda grass pasture the same way you manage a Bahia grass pasture, you probably end up with a not very successful Bermuda grass field. Whether it's mechanically harvested, whether it's grazed, the nutrient management should be specific to that particular species. And this is the University of Florida recommendations. That's another thing that's a little tricky because if you look at so I'm assuming here, phosphorus and potassium is always based, fertilizer recommendations is always based on soil test. And I'm going to talk about soil tests as well. So the amount of recommended P and K will depend on the soil test results. Nitrogen is a different story. Like I said, for Bahia grass, it's based on the how much forage the producer wants to produce. That's, in other words, is it a low input system or is it a high input? Do they need to push the system to produce more forage? So more nitrogen will be required. So the requirements are different depending on the species. And one thing that we always run into, they are not necessarily economical. Look at Limpo grass. Very rarely we see anybody applying 120 over 100 pounds of nitrogen to the acre. So this is the recommendation. Doesn't necessarily mean this is going to be the most economical option for every single operation. So this will be a user decision. We provide information, but this will vary depending on other economic factors. Chris here can help me But depending on how the economics go for that particular year, those things can change. Some certain years it might be more economical to apply more fertilizer. I don't think that's the slide, but also there's also, so when you apply, for instance, 50 pounds of nitrogen to the acre, 1 year, you may get X amount of tonnage, extra tonnage produced. If the environmental conditions are not ideal, the following year you might get half of that. I have a slide, I don't think I have in this presentation, that shows the amount of pounds of dry matter produced per pound of nitrogen, and then varies. I've been measuring that every year for the past 10 years, and it can vary a lot. So fertilizer is just one component in the production system. Environmental factors can also affect. So a very common question that producers ask us is, well, if I apply 50 pounds, how much more tonnage or how much more the nutritive value of this particular pasture can improve? And the answer is always, it depends. Not because we don't know the answer, because it really depends on other factors like environmental rain, that previous year, how the winter was. So again, soil fertility is just one component in the big picture. I think we all saw, you all probably in this room seeing this concept, but bringing back to cow-calf production, a very common practice for most producers, because it's fertilizer is such a costly input. They only focus their fertilization management on nitrogen. But what this figure is trying to demonstrate, that the production will be limited by the nutrient that's deficient in the soil. It could be nutrient, or it could be, in this case, it's water, like I said, environmental factors. So in a situation, especially for mechanically harvested systems that are, the fertilizer management is based on nitrogen only, most likely some of the other nutrients, phosphorus, potassium, can be deficient. So in other words, they are not getting the full benefit of nitrogen fertilization, because what's limiting the yield or the production potential, it's probably another nutrient. So we need to take a more holistic approach when we look at soil fertility. It's not nitrogen. The reason why we look at nitrogen is because in terms of response, nitrogen is, in terms of tonnage produced, nitrogen is probably the nutrient, the most important one. So you apply nitrogen, you see an immediate response in terms of growth and sometimes even nutritive value. Phosphorus and potassium might not be the same. They might be associated with other factors that are equally important. They might be associated with persistence, for instance, but you don't visually see that increase in production immediately. The same is valid for lime. You don't see, by applying lime, you don't see a boost in forage production, but lime is equally important as nitrogen. So let's talk a little bit about soil testing. Just want to make sure I'm not going through. It's not a new concept. Scientists have been spending a lot of time developing better soil test tools since past 50 years. The tests need to be quick, because most labs, they run a large number of samples. I don't know how many of you understand how the soil test is, how the procedure happens in the lab, but basically involves, they scoop a small amount of soil into a vial. It could be something like this, or it could be a tube. They add a solution, they shake the sample for 5 minutes, a very fast extraction, they filter, and that extract is analyzed. So it's a very simple, fast, because that's how it needs to be. From the practical standpoint, labs cannot do a very elaborate testing. But because it's fast, it's cheap, there are some limitations. Forget about reading. What I'm trying to say here is that when you do that, when you shake for 5 minutes and you analyze phosphorus, nitrogen, whatever nutrient in that extract, that's not the total amount of that nutrient present in the soil. What the solution is trying to do is mimic what the plant sees as available. So the solution and the extraction procedure is supposed to mimic what the plant's roots are doing in the soil. I'm going to skip this. What the bottom line is, in terms of soil testing, I said it's being developed more than 60 years ago, but it's underutilized. Even though we are all here involved in extension, we always talk about the importance of soil testing. There are some limitations, but it still is the best tool to manage for soil fertility. It's a very underutilized tool. For instance, the only thing I want you to pay attention to this picture is, if you look at the percentage, this is a survey that was conducted in the Southeast United States and they went through soil test results, and basically 50% of those, the samples, I don't remember exact, but it was a large number of samples, I don't remember. It was thousands of samples that were analyzed. About more than half had low pH. In this case, they're considering low pH anything below 6. In Florida, it would be pretty much the same. Florida was included in the survey. So managing the soil pH, soil acidity is probably the #1 most important property that's being mismanaged for various reasons. First of all, is because, like I said, soil test is not being utilized. How can you apply lime or make it help with the lime recommendation if the soil has not been tested? And because you don't necessarily see that immediate increase in forage production after a lime application is different than hydrogen. Collection. So when you finally convince people that the soil test is important, collection is a very tricky step in the process. It seems like very obvious how to properly collect a soil sample, but you'll be surprised at how many people don't collect the sample properly. It's a labor-intensive, especially if we're talking about large operations, it's a very labor-intensive process. But otherwise, if the samples are not collected properly, doesn't make even sense to test the soil, because the sample doesn't represent what the area of interest is supposed to be. And what I want to say is, I realize that I probably have, my presentation could probably be the whole day in service training. Recently, we switched over from Melic 1. So when I mentioned that solution that reacts with the soil for 5 minutes, that solution has a name. You probably heard about Melic 1, some people call double acid. Recently, about 2 or 3 years ago, Florida, and each state, by the way, has that standard solution. So if you go to Texas, for instance, they use Melic 3. If you go to other states, they might be using another method that's called Braid. Recently, University of Florida switched from Melic 1 to Melic 3. So the solution is different. Melic 1 was a sulfuric acid and hydrochloric acid, very diluted acidic solution. Now we switch to Melic 3, which consists of all these different chemicals. There's multiple reasons why they made that change, but primarily was to address soils with high pH. Melic 3 is a very poor extractor under high pH conditions. And a lot of the vegetable areas, and the citrus areas as well, because of the irrigation, the soil pH were gradually increasing. So they switched to Melic 3 because it was a better extractor under high pH conditions. So when a producer asks for your help to test the soil and they understand the sample needs to be collected properly, handled properly, the decision in terms of what labs to submit, it can vary. It doesn't necessarily need to be University of Florida lab, and we know that we also have some issues with extension soil test lab engagement. It can be a commercial lab, but it's important to keep in mind that a lot of these factors can change depending on the lab that they utilize. So the extraction procedure could be different, and the units they report could be different, but what I think is more important is the lime and fertilizer recommendation can be quite different. And they often ask us, why I send my samples to Waters Lab in Georgia, and I'm getting a completely different fertilizer recommendation compared to University of Florida. You can take a look at this slide one more time at home. I'm running out of time. But this is one sample, the same sample that I submit to 5 different labs, and here are the different fertilizer recommendations. The exact same sample, the results can vary significantly. Usually, if you send to a commercial lab, the fertilizers recommendation are going to be much higher. So producers often ask us why, and they always relate it to that could be an environmental factor. So we're trying to prevent them from applying fertilizers so they don't cause any water quality, but it's not. There are different fertilizer philosophies, and usually land-grant universities, we use what we call this sufficient level of available nutrients. So basically, you can read that more. Joe is looking at me, I'm probably running out of time. Some soils in some regions in the country, the main goal when they apply fertilizer is to build up the soil, the nutrient content in the soil. Imagine in our sandy soils this time of the year, our sandy soils that have very limited nutrient holding capacity. So we cannot very rarely we can afford to improve that nutrient content in the soil. It's very difficult and very costly as well. So instead of improving the nutrient content in the soil, what we target is the plant requirement. So if a nutrient test medium or above, to us means that the plants will likely not respond favorably to fertilizer application. So how is that those levels, those ratings are determined? How do they tell, when you see the soil test result in the next, you see, sometimes it's not the values, but what's important is how they are rated. By the way, this is MEDIC 1 result. So in MEDIC 3, you don't have the very high, the very low, and the very high. Only you're going to see the low, medium, and high. How these different categories are developed? It's a two-step process to determine this. The first step is the scientists have to develop correlation and then calibration. So basically, that soil, I said the soil test procedure is supposed to mimic what the plants do in the soil. That's the correlation. So whatever chemical I'm using to react to my soil with needs to mimic what the plant is doing. So there's a lot of experiments and science involved in developing those chemicals. This is the correlation. And the calibration is once the soil test procedure is well correlated with the plant response, which usually that's determined in the greenhouse condition. Now is that the calibration is okay. Now I know that this is 20 parts per million of phosphorus in the soil. Is that low, medium? So they do this traditional soil fertility experiments to see plant response under different nutrient levels in the soil. Basically, this is an example for phosphorus, and this is yield. This is a hypothetical. Well, let me change to another one because this is the actual data. This is phosphorus in the soil, and this is percentage of relative yield. So the maximum yield will be 100%. So everything that's between 50 and 75% of the maximum yield will be considered low. So this is half of 75% of the maximum yield. This will be the low levels of phosphorus in the soil. And the same thing goes on for medium. So medium would be something about 75 to 100%. Whoops. And that's how those different rates are determined for different elements. So this is for phosphorus. The same thing is done for potassium and calcium. I think this is going to be my last concept. I'm way more. I have way more information. I guess I underestimated my ability to talk.
You'll be the last concept.
Because this is very confusing. So we talk about fertilizer recommendations. Fertilizer recommendations are based on that document that everybody knows, the Bible SL 129, which is definitely not user-friendly. So don't share that with. Maybe you don't want to share that with the producers. But so we talk about fertilizer, and I mentioned that soil pH is a very important property, but I did not say anything about pH. And I want to talk about this number. This is a very confusing part of the soil. I think this is Ed's. Yeah, Ed G's. Sure. So I covered the producer here, not to just claim who the sample was. So you're going to see this is universal for the soil test report, and this is medically. So you see that you don't have the very low and the very high. They decided to make it a little simplified. This is the actual pH of the sample, 4.9. Target pH. Probably this sample was likely labeled as Bahia grass. It was Bahia grass because I see there's a tissue concentration here. Phosphorus soil has high pH, there's no need for tissue. I'm probably not going to have time to talk about tissue, but I want to talk about the pH. So, the target pH for Bahia is 5.5. Where do I find this information? SL 129. Target pH is that my pH, soil pH is 4.5. How much lime do I have to apply to increase the pH from 4.5 to 5.5? Well, you probably heard a lot of producers say 1 ton of lime per unit of pH. This never worked. The reason for that is soil, they have a ability that's called buffering capacity, which is basically resistance to change. So for instance, Joe has a very high buffering capacity. He's a very backward person. Some soils are like Joe. They don't change that much. Some soils are more open-minded like me. They go both ways. So what are the properties that determine the buffering capacity? Basically two things. Organic matter content and clay content. Our soils have very poor, almost absent clay content, very low clay content, and very low organic matter. So our soils can change very easily, which is good for us. We can manage both ways. This buffering capacity, and the AE, by the way, means Adam and Evans. This procedure tells us how much lime or the buffer indirectly measures that buffering capacity. So what that is a solution that has a pH 8. So again, everything is happening in the lab. Soil reacts with the solution that has a pH 8 for a very short period of time, and then they measure the pH afterwards. So for instance, this soil had a 4.9, so the soil has a lower pH. It's most likely it's going to be lower than 8. After the soil reacts with the solution, the pH of solution is probably going to be less than 8. So depending on how far from 8 the solution is, that is a direct measurement of buffering capacity. So the lower this number is from 8, the more lime the soil will require. So you might have a soil here that has a pH 4.5, and you see the recommendation for lime here is 2,800 pounds of, almost 3,000 pounds of lime per acre. But you may have a soil that has a pH 4.5, and you're going to see the recommendation might be half of that, might be 1,500. Why is that? Lower pH should require more lime to bring the pH to 5.5, but it might be the buffering capacity might explain why. So really, producers that don't necessarily need to understand this, it might be a little bit too much, but for us that are helping them interpret, they might ask us why a soil that has lower pH has a lower lime recommendation compared to this, and this has to do with the buffering capacity.